Hello and welcome to the Chosen Few, the one and only place for you. My name is Isabelle Santine, though you probably knew me by a different name. And today I am talking about fractals. More specifically, the task of fractal rendering and why it's so hard and what I'm doing to kind of make that easier and better. Our story today starts with about a year ago, maybe a year or two ago, I was interested in creating pre-rendered super resolution fractal images. So what I mean by that is basically my goal was to pre-render or pre-compute an image of this entire very complex shape at a very high resolution, so that way people could browse it and view it without having to spend a lot of computational effort to do so. Let me go ahead and show you guys this image right here. So basically what this GIF on the screen is a demonstration of quad tree image compression. And what that basically does is it splits the image in iteratively into quadrants, and then quadrants of quadrants, and so on. And the idea is that at each step, we basically take the average color of this whole of each quadrant, and if the total error between the color of each subquadrant and the color of the quadrant of considerations are different enough, they get split into more quadrants. And as a result, we get this pretty efficient compression algorithm that spends most of its effort on the most detailed areas of the image. So as you can see down here in this portion, there's a bit of trouble that it has with capturing the gradient of the sky. And that's because it is focusing on the more detailed portions of the image right here, using some kind of predefined error value. So yeah, I was inspired by this image compression technique to basically not only compress these super resolution fractal images that I wanted to create, but also to basically speed up the computation as well. Because the thing is, this whole white area right here, which as you can see is a large portion of the image, this is actually the most expensive area to calculate per pixel, because these are the pixels. Basically, to calculate this fractal, I have to run a looping calculation that at each step, I basically check, is this point in this space within this boundary, within this region. And these white pixels mean that they don't go out of the region at all during the calculation, during the loop. What that means is that you traditionally, with a naive pixel per pixel rendering of this image, you spend most of your time rendering these white pixels. But the cool thing about using the quad tree method that I explained just now is that you can basically just calculate a few sub-areas of this large white blob. And based off of that, if most of the pixels in this region are white, or in each of these four regions are white, then the entire region must be white. And if it's not, then we split it into subregions and start calculating those subregions and so on. So it's kind of a recursive function. So yeah, that's basically what I've done here in this prototype implementation of super resolution fractal image rendering. And what I have calculated here before, actually just a few minutes before doing this presentation, before sitting down and recording this, I've calculated a 65,000 by 65,000 pixel image of the Mandelbrot set. So let's just go ahead and zoom in and out of this thing. So for efficiency, I sort of, as we're browsing around, I render a low resolution version of the image. And then when I stop moving around, that's when it starts basically streaming in the higher resolution version from the disk. And basically, how I've designed this file format is that you can stream in detail as you need it. You don't even have to store any of the image in memory while you're trying to view it. The cool thing is that we can just keep zooming in, and detail just keeps streaming in as we're doing this. And my idea for a future idea of mine for this application, for this prototype really, is that under a certain circumstance, such as maybe you want to download one of these super resolution images from the internet, you can view a low resolution copy of the image while all of the rest of the detail is streaming in. So you get the low resolution copy first, and then it iteratively gets more and more detailed as more and more data gets downloaded. So I thought that that was a really cool advantage of how I'm choosing to both render and store these images. And why don't we actually do a little bit of a comparison of file sizes as well. So this file right here is the image file, and as you can see, it's around 108 megabytes. And this is for the entirety of the image. If we go to my previous attempt at a fractal render of the same resolution and same per pixel bit depth, this PNG was created from hundreds of 64 by 64 tiles. And if we go to the details here, this image is only a quarter of the resolution of the one that I was showing you in my custom prototype viewer. And it was almost double the size, almost 203 megabytes. So that's kind of insane. It means that this quad tree compression not only cut down significantly on the amount of computational work I have to do to render the image in the first place, but it also cut down significantly how much data we have to store on the disk in order to store it. So that's pretty great, in my opinion. Basically, the kind of workflow for generating these images goes like this. So you basically start by creating a Surge archive, which is a directory that stores a root image, which is this _.surge file. So it starts off with a 16 by 16 tiling of the Mandelbrot set image. And based off of that, it creates a bunch of other sub-images. It renders out all of the tiles that contain any further detail. So these are those tiles right here. And then after generating this archive directory, what you do is you optimize the Fractal, or the Surge archive, and make it streamable. And basically what that does is it collates all of those tiles, as well as the root image, and it collates it together in such a way that you can stream in detail linearly with the length of the file. So that becomes an SSRG, or streamable Surge file. And yeah, using this technique, I'm hoping to actually break a world record with the largest rendered image of the Mandelbrot set ever, which I think will be really cool. And I'll actually show you how that's the progress on that. So this is the largest image that I haven't finished yet, basically. So it looks finished from the outset, but here's the catch-22. This is a 4K image right here, how we have it. And the thing is, each of those 4096 by 4096 pixels is itself a 4K by 4K square image. So let me show you what what the scale of that even means. It's really insane. So if I zoom into here, it looks pretty blocky right now, but as soon as all the detail streams in, isn't that insane? And watch, I can just keep zooming into this. Watch. I can just keep zooming into this, and detail just keeps streaming in. And voila. Look at that. It's still 4K level resolution detail. That's insane. And I can just literally keep zooming into this. Eventually we'll run out, but I don't think we've hit that threshold yet. And there we go. Look at that. We still haven't run out of detail. We're still not upscaling yet. That's the raw scale of the image that I'm rendering. To put it into perspective, it's a 2 to the 24 by 2 to the 24 square image of the Mandelbrot set, which is just enormous, as you can see. I can just keep zooming into this for probably a little while longer. Let's try it. Yeah, just see, detail just keeps coming in. I think this is whereabouts it runs out. But it's just insane to me that you can basically, from that 4K image, you can zoom in by a factor of 12 separate times before you get to the point where you run out of resolution. That's just crazy. And yeah, the other cool part about how I'm doing things here is that my idea for this was to allow for real-time recoloration of the fractal image at very little expense. So no need to recalculate all of the expensive fractal calculations. You can literally just pull in the iteration counts of each pixel and then redo the coloring on the fly as it streams in from the disk. I'm just so excited to have this prototype to the point where I can show it to someone because it's just literally insane, right? Isn't this cool? But yeah, that's all I really wanted to show you guys for now. I'll keep you guys updated on the progress of that massive render. Right now, I have only a small portion of it done. Right here we can see it's currently 6.1 gigabytes in size. So I'm probably going to need to pull out my 2 terabyte drive eventually and use that to kind of keep this under control, because otherwise I'm just going to run out of disk space really quickly. But yeah, that's all I really wanted to show you guys. I hope you guys enjoyed this video, found it interesting. Make sure to subscribe to the Chosen Few Software channel down below. And yeah, I'll see you guys next time. Bye-bye.